So first I'd like to go ahead and begin with the four key properties of the heart that allow it to conduct and generate electricity. The first term we're going to discuss right now is called automaticity. Automaticity is the ability of the myocardial cells to spontaneously generate an electrical impulse without being stimulated by another source. What this means is that you could literally separate the heart from the central nervous system. And due to the cardiac's ability to have automaticity, that means that it will continue to beat for a short time. It will continue to depolarize itself for a short time, even after not being stimulated by the central nervous system. That is the property of automaticity. The next property is called excitability. Just because you stimulate the response through automaticity or from the central nervous system does not mean the cell is going to respond. So excitability is the ability of the myocardial cell to respond to this impulse. This is the key word right here. It has to respond to the impulse itself. The next property is conductivity. Just because a cell generates electricity and it can respond to the electricity, it has to conduct that electricity to propagate it to the next cell, to the next cell, to the next cell, and so on. So conductivity is the cell's ability to receive an impulse and then transmit it to another cell. That is conductivity. The final property is contractility. Contractility is the cell's ability to contract when it is stimulated by an impulse. Now the key here is that for contractility to occur, there must be myofibrils or muscle cells. These myofibrils are muscle cells. Every other cell in the heart has the ability of automaticity, excitability, and conductivity, but not every cell in the heart has the ability for contractility. Only muscle cells or myofibrils have the ability for contractility. The conductive pathway through the heart, when we talk about the conductive pathway, we're talking basically about the SA node and the internodal tracts and the AV node, and we'll get to those in just a second. It does not contain myofibrils, which means that they cannot contract. Now, this is a good thing because these cells that don't contract are only the superconductive high-speed transmission cells. They are not designed to contract. They are designed to get the signal from point A to point B as quickly as possible. So to do this, there are a lot more gap junctions. And if you remember what gap junctions are, those are the little holes in the intercalated discs that allow the ions and the electrical impulse to propagate down the cell. So because there's so many more gap junctions, it speeds up the electrical transmission, making this the high-speed conduction system. So we're going to start off here with the electrical system of the above the ventricles. And these are the ones we're going to go over. We're going to go over the SA node, the internodal pathways, something called Bachman's bundle, and we're going to go over the AV node. The SA node. First of all, the SA node, as you can tell, is this little sucker right up here. You can see it right there. This SA node is located up here in the right atrium, in the upper part of the right atrium. It's just below, located just inferior to the superior vena cava. The SA node is also considered the heart's primary pacemaker. And since this is a primary pacemaker, it will have an intrinsic rate, also called an inherent rate, of 60 to 100 beats per minute. What intrinsic or inherent means is that under normal situations, it will typically depolarize between 60 and 100 beats per minute. There are 3 pacemakers that are in the heart. Each one of them have an intrinsic rate. In this case, the SA node's intrinsic or inherent rate, because those two words are synonymous, is 60 to 100 beats per minute. The internodal pathways are 3 pathways that leave the SA node. As you can see here, they leave the SA node, and then they approach the AV node. These 3 internodal pathways right here are located all within the right atrium. Now, there are 2 tracts that depart the SA node, 2 tracts that approach the SA node, the AV node, but you can see that there's 3 of them here. The tracts are classified as a anterosuperior tract, which would be this one up here, but this one is also known as the fast tract. This one down here is known as the slow tract. It's also called the posterior inferior, but don't just worry about the fast tract and the slow tract. So this would be the fast tract. This would be classified as the slow tract. What happens whenever these tracts arrive at the AV node, as you can see right here, the fast tract comes down, it will depolarize quicker, and typically it will reach the AV node first. When it does that, there is another depolarization that can occur up in this direction because the slow tract is taking longer to reach the AV node. The fast tract will make it all the way down to the AV node and continue depolarizing in this direction, and it will also continue to depolarize in that direction. And the reason it does that is because there are cells that can be depolarized. So if a cell can be depolarized, it's going to continue depolarizing. It doesn't matter in what direction. So what happens is the signal comes down the fast tract and it depolarizes down into the AV node. But if these cells here have not depolarized yet, the signal will start to travel up backwards up the slow tract. Normally what happens is the signal that's propagating down the slow tract right here meets up with the fast tract depolarization that's trying to go backwards up the tract, and it actually cancels itself out. So it meets right here, and the signal stops because 2 cells or 2 areas have been depolarized and they reach each other. They're not going to continue depolarizing. Now this happens in 99% of the people. 99% of the time, this little system right here occurs. Not everybody has two tracts that approach the AV node. There are only 10% of the population have this system right here. There's only 10%. Most people, this tract up here will just terminate somewhere out here in the atrium. It doesn't actually reach the AV node itself. The AV node has three separate areas. The AV node has something called a transition zone. It also has something called a compact zone. It also has something down here that's called a trigger zone. It's called a trigger zone. Now the transition zone, when I talk about the transition zone, it is actually located on like the surface of the AV node itself. It's a very small amount of tissue. So first we're going to talk about the transition zone. There's a very small amount of tissue on the tip or the covering of the AV node. Now this area right here, this transition zone right here, is covered or is primarily made of autonomic fibers. What this means is, if you remember, automaticity is a cell's ability to generate its own impulse. So the transition zone is full of these cells that have the ability to generate their own impulse. Because the transition zone is composed of autonomic fibers, it is very arrhythmogenic. Which means it can generate its own impulse or generate its own rhythm very easily. The next zone is the compact zone. This compact zone is considered the core of the AV node. Histologically, the compact zone is very similar to the SA node. Which means if you end up with a junctional rhythm, this is probably an area that it would come up to. This is the area that would be affecting that. This would be the nodal cells, and we'll get into what a nodal cell is later, of the AV node. This is the nodal cell itself. Now, the compact zone also has an intrinsic rate. And this is an intrinsic rate of 40 to 60 beats a minute. Which means that the compact zone and the AV node itself is considered the backup pacemaker. So its intrinsic rate is 40 to 60 beats a minute. And also what happens in the compact zone, this is where the transmission or the impulse that travels from the SA node through the AV node, as it travels through the AV node, the compact zone is where the signal is slowed down. The reason it's slowed down is because it needs to allow for atrial contraction. The last area is called the trigger zone. In the trigger zone, this is where it kind of transitions from the compact zone into the His bundle. The trigger zone is also important because this is where the transmission speeds up. So it's slowed down through the compact zone to allow for that atrial contraction, but then once it hits the trigger zone, it speeds up again. So let's come over here to the picture. The signal comes down here. Let's say it comes down the fast track. It goes through the transition zone, and as it hits the compact zone, the signal is very much slowed down, and it takes a lot longer for the signal to get through here. Once it gets here to the trigger zone, then it speeds up again and speeds through the His bundle down into the bundle branches. The atrioventricular junction itself is comprised of the AV node and the His bundle, or bundle of His. The His bundle itself, there's a couple different purposes for this one. First of all, the His bundle represents the only route of communication between the atria and the ventricles. Only route of communication between there, which means if there's a blockage here at the His bundle, there is going to be no communication between the atria and the ventricles. That is the purpose of the His bundle. Part of the His bundle is found in the right atrium, and then it will go past or through something called the atrioventricular septum, which is a non-conductive wall between the atria and the ventricles. The His bundle is the only route of communication through that. So it'll go from the right atrium through the atrioventricular septum, and the His bundle will actually terminate just on the inside of the interventricular septum. At which time, after it terminates into the right and left bundle branches. So that finished up with all of the supraventricular electrical components. So now we're going to start talking about the ventricular electrical system. We're going to talk about the right bundle branch and the left bundle branch, and then we're going to talk about the anterior and the posterior fascicles, and then the Purkinje fibers or the Purkinje network. Most people just talk about the right and left bundle branches, but in this class we're going to go a little bit more detailed and discuss the bifurcation of the left bundle branch into the anterior and posterior fascicles. So first let's start with the right bundle branch. The right bundle branch, obviously it starts at the bifurcation of the His bundle, so it begins at the bifurcation of the His bundle and it terminates at the Purkinje. Specifically the Purkinje in the right ventricle. Whoops. In the right ventricle. Let's talk about the left bundle branch. The left bundle branch travels a very short distance, and really the left bundle branch is shorter than the right bundle branch itself. So the left bundle branch starts at the bifurcation of the bundle of His and terminates at the bifurcation to the anterior and posterior fascicles. So as you can see here, the left bundle branch begins here, but it actually stops down here. It doesn't actually continue all the way to the Purkinje network. So the right bundle branch does continue all the way down to the Purkinje network. The left bundle branch does not. Stops here where the fascicles, where it turns into the two fascicles, basically. Let's go ahead and talk about the fascicles right quick. This is new information to a lot of people because at earlier or simpler levels of EKG or rhythm interpretation, a lot of people don't discuss the fascicles. They just say the left bundle goes all the way down to the Purkinjes, and that's not entirely accurate. So we have two different fascicles. We have a posterior fascicle and an anterior fascicle. Generally speaking, the anterior fascicle depolarizes kind of the anterior aspect, and the posterior fascicle depolarizes the posterior aspect. Generally speaking, it's a little bit more detailed than that, which is easy information to find if you look in a more advanced medical book or a cardiology book. But for our purposes here, just keep it as simple as that. I don't want you guys to have too much information. So let's talk about the posterior fascicle first. The one thing I want to first of all mention is that this picture here is not entirely accurate. What it says here is that the left bundle branch turns into the posterior fascicle, and it has this fiber that runs down this way with all these little fingers that come off of it, and that's not entirely accurate. The way that the posterior fascicle actually works is that as the left bundle branch starts to turn into the fascicle, the fascicles come off this way, kind of like fingers or ribbons off of the left bundle branch. So it's not one fiber that comes off this way, it's a whole bunch of little fibers that come off that way. Now the reason this is important to understand is because when you start talking about posterior and anterior fascicular blocks on a 12 lead, there is a more common anterior fascicular block than a posterior fascicular block on a 12 lead. And the reason for that is because if you look at the anterior fascicle, it goes further down and straighter as a cable than the posterior fascicle, which are all these fingers coming off of here. The reason that's important is because if you block a little bit of tissue here, you're going to block the anterior fascicle. On the other hand, if you block a little bit of tissue here, you're still going to have the posterior fascicle is still going to be able to depolarize the posterior aspect of the heart. So it's harder to have a posterior fascicular block than an anterior fascicular block. That's why it's important to understand the true structure of the posterior fascicle. It's like a bunch of fingers or a bunch of fibers coming off of a bunch of ribbons basically coming off of this left bundle branch right here. So basically the posterior fascicle, its responsibility is to depolarize the posterior and the superior aspects of the left ventricle. So it's a depolarization of the posterior superior or the superior posterior area of the left ventricle. Like I said, very difficult to block because it's so widely distributed. So now let's look at the anterior fascicle. Anterior fascicle is more like a single strand of conductive cells that goes all the way down to the Purkinje network. The posterior fascicle terminates at the Purkinje network. The anterior fascicle terminates at the Purkinje network. So the anterior fascicle depolarizes the inferior and anterior aspect of the left ventricle. and it's more easily blocked. Than the left posterior fascicle. Like I said, the anterior and the posterior fascicle also terminate at the Purkinje network. So let's talk about the Purkinje fibers themselves. The Purkinje fibers are located at the terminals of the right bundle branch, the left anterior fascicle, and the left posterior fascicle. Notice that the Purkinje network are not the terminals of the bundle branch on the left side, because the left bundle branch only goes from the His bundle down to the posterior fascicle, anterior fascicle bifurcation. The left bundle branch does not make it down to the ventricles themselves. Now, the Purkinje network is responsible for depolarizing the ventricle itself. So they're responsible for actual depolarization of the muscles to allow for ventricular systole or ventricular contraction. The Purkinje network is the tertiary or the backup to the backup pacemaker. So they're the third pacemaker of the heart. They too have an intrinsic rate of 20 to 40 beats per minute. So just remember this intrinsic rate stuff. There's a lot of different numbers that I've seen in a lot of books. Some of them will say, well, higher up the Purkinje network, closer or higher up the bundle branches, they have a 25 to 35 or whatever. It kind of goes all weird. Just remember that the Purkinje network has a 20 to 40. The AV node has a 40 to 60. The SA node has a 60 to 100 beats per minute intrinsic rate, and you should do fine just like that. If you're reading a material that you're being tested on that gives you different numbers, please use those numbers, but these are kind of accepted as common knowledge. So let's go ahead and start talking about depolarization of the cell. So you kind of now hopefully understand the conduction system. Now let's talk about the depolarization of a cell. When a pacemaker is at rest, it is considered to be in a state of polarization. Now, what we mean by a state of polarization is that the outside of the cell is primarily going to have a positive charge. The inside of the cell is going to have a primarily negative charge. This is at a state of rest. This also means that there is no electrical activity. So there's no electrical activity going on right now, and it is at rest. When a cell is at rest, it is ready to do work. All of the ions are on the proper side in the proper quantities, and it's waiting for an impulse to start moving ions and to start doing work. So when a cell is in a state of polarization or it's at rest, what that means is that on the inside of the cell, which is primarily negative, there are large quantities of potassium, phosphates, which is a 3 negative, and sulfates, which is a 2 negatives. So there's a lot of stuff inside the cell. The one we're worried about for right now, we're going to talk about the potassium on the inside of the cell. Also, during a cell state of polarization on the outside of the cell, there are high concentrations of sodium and calcium, which is a 2+. What we're going to worry about when it comes to cellular depolarization is the sodium and the calcium. So we're going to worry about both of those. The phosphates and the sulfates during cellular depolarization, we're not going to get that detailed to worry about those. So the three primary ions I want you to worry about is the sodium, the potassium, and the calcium during the state of depolarization. Depolarization of the cell occurs as an action potential. The action potential itself is the process of the cellular depolarization. So what is the action potential? It is the change in the electrical charge of the cell. And that means that it's the change from resting to depolarization, the process of repolarization, back to a state of rest. This is based on, this whole action and everything that occurs is based on the sodium and the calcium, which are both outside the cell, and the potassium, which is inside the cell. Before we get to the action potential, what I want to describe right quick is something called the all or none principle. The all or none principle becomes important when we start talking about cellular depolarization. What the all or none principle basically means is if a cell reaches threshold, and we'll talk about threshold in a minute, if a cell reaches threshold, it will depolarize every single time. Every single time. There is no such thing as a partial depolarization of a cell. If that cell reaches threshold, which means it has the ability to depolarize, it will depolarize every single time. Now, while every cell will depolarize if it reaches threshold, not all cells have the same threshold level. And we'll talk a little bit more about this later. So let's talk about the action potential itself. First of all, this is kind of what the action potential will look like. You can measure the electrical, the millivolts basically inside the cell and near the cell membrane. So what we're going to talk about first, there are 5 different phases of the action potential. Okay? What you start with is down here, and this is negative 90 millivolts. We'll just go with it. This right here is considered your resting potential, or your resting threshold, or whatever. Okay? This right here is called your threshold potential. And then up here you have 0 millivolts, which means it's breaking even, and then you have a positive up here. So back to the all or none principle. When an impulse hits this cell right here during its resting phase, because this right here is a resting phase, the impulse has to depolarize the cell enough to exceed the threshold potential. What happens if an impulse hits this membrane and it goes up to here and it doesn't quite reach that threshold? The cell will not depolarize. The cell will stay just like it is at resting. It has to reach, that impulse has to be strong enough to depolarize that cell for it to reach the threshold. Now, once it reaches threshold, it takes off and it continues to work by itself. But the impulse has to be strong enough to get it to threshold. Very similar, it's like turning on a car. If the battery is not strong enough to turn the engine over for it to catch itself, then the engine will never start. But if the battery is strong enough, once it starts, you don't need the battery to keep starting the car again. The battery will kind of help the car keep going. This is very similar. Right here, the impulse, the electrical charge, was not strong enough to get this sucker going, to get the cell to depolarize. But over here, it was. So what we have here is a cell that's in a resting state right here. Okay. What happens is when this impulse hits this cell, and once this cell reaches threshold, what happens is the very first phase is called phase 0. So phase 0, which is this part right here, phase 0 is your rapid depolarization phase. Now what happens in phase 0 is, remember where the ions are. Sodium is outside the cell, potassium is inside the cell. Once this cell reaches threshold and it continues to depolarize, fast sodium channels open. And since sodium is in higher concentration outside the cell than it is inside the cell, these fast sodium channels open, sodium rushes in to the cell. There's a lot of sodium out here. It rushes into the cell. What that does is, if you remember, the inside of the cell is primarily negative. As you have a lot of this positive sodium right here rushing into the cell, it causes the inside of the cell to change from a negative voltage or millivoltage all the way up to a positive millivoltage. Now that the cell depolarizes, if it has the ability to contract, it will. So now that it depolarizes, it does its job. Whatever the cell is supposed to be doing, this is the work, this is what it does. Now notice it only goes up to a certain point. So what happens is, after the inside of the cell reaches a certain millivolts, and we'll say it's positive 20 here, these fast sodium channels close. So in phase 0, the fast sodium channels open, sodium rushes in, to cause the inside to become positive. After it reaches a certain millivolts, it closes. This uses positive 20 millivolts, but it could, depending on the cell. This is just a general statement here. So depending on where it stops here, and all of those fast sodium channels slam shut, because you don't want the sodium to keep rushing in there, because you're just going to cause more damage to the cell. Once this occurs, you end up having something called phase 1. Phase 1 is the early rapid repolarization phase. During phase 1, fast sodium channels close, which slows the influx of sodium. Because of this, this causes a slight repolarization of the cell membrane, but it doesn't repolarize completely. It's just a slight repolarization. To occur. Now, the cell will stay depolarized. As you can see here, it depolarized, right? You had the impulse that hit, sent it up to threshold, it reached threshold, fast sodium channels opened during phase 0, it stopped it, and as it comes back down, this part right here is your phase 1, your early rapid repolarization phase, but it doesn't completely repolarize, not until you get way over here. So it kind of starts to repolarize, but then it stops during the repolarization. The process is actually slowed down, and it actually stops. What happens next is something called the plateau phase. So here we have phase 0, here we have phase 1. This is actually phase 2, which is the plateau phase. Now, this occurs mostly in cardiac tissue cells that are needing to contract. So this is where muscle fibers will need to contract to allow for ventricular contraction to eject the blood. So sodium rushes in over here. It closes it here. Sodium can't be let in here, so there's another ion, which is a calcium, which is a 2+ ion, that is also outside the cell. What happens during phase 2 is that calcium will then slowly enter the cell, and your potassium is in here too. Calcium will slowly enter the cell to allow for this prolongation of this depolarization. If there was no calcium here, your depolarization right here, your plateau phase would be a lot shorter because it would have to depolarize quicker. But fortunately, the calcium is there to actually prolong and allow for muscular contraction. Calcium is the primary ion necessary for muscular contraction. Without calcium, your muscles can't contract, is the bottom line. You need the calcium to allow for muscular contraction. So the sodium rushes in, depolarizes the cell. In phase 1, it stops, the gates close, and it kind of plateaus. Calcium allows for the prolongation or the plateau phase here. So in phase 2, the plateau phase, calcium slowly enters the cell. Which causes it to plateau, which causes the repolarization to plateau. The next phase that occurs is the rapid repolarization phase. So if you remember, let's go back, we had sodium on the outside here. Sodium rushes in once you reach threshold. It closes off the fast sodium channels. It starts to slightly repolarize, but a plateau occurs because you have calcium that rushes in as well. Now you need to repolarize the cell somehow. If you open up more sodium channels or more calcium channels to try to repolarize the cell, all that's going to happen is more sodium is going to rush in or more calcium is going to rush in. So your body has to get another positive ion, potassium, out of the cell. Now, potassium is in higher concentrations on the inside of the cell as compared to the outside of the cell. So if you want to repolarize quickly, you want to use a passive process where you can get a positive ion out of the cell very quickly. You can't use sodium or calcium because those are in higher concentrations on the outside of the cell. Potassium is in higher concentration on the inside compared to the outside. So to repolarize quickly, this is phase 3 right here. To repolarize quickly, you open these fast potassium channels and potassium will rush out of the cell. What that does is it causes the cell to become increasingly negative until you finally get down here to your resting phase again. So during phase 3, calcium channels close, keeping the calcium from coming into the cell anymore. And then potassium channels open to allow the outflux of potassium for repolarization. So what will happen is the inside of the cell, as the potassium leaves, the inside of the cell will become, as you can see here, increasingly negative. It's heading further and further down into this negative area right here. That's what happens during phase 3, which is the rapid repolarization phase. The last phase is phase 4, which is considered the resting phase, or the period between the action potentials. Anyway, phase 4 is this area over here. So you had phase 0, then you had phase 1, then you had phase 2, then you had phase 3, and now we have phase 4. In phase 0, you have your sodium rushes in. In phase 1, the sodium channels stop, but the calcium channels open. In phase 2, you have your calcium flowing in. And at the beginning of phase 3, you have the calcium channels closed, but the potassium channels open, and then potassium rushes out. When you get down here to phase 4, you have officially reached, you have come back down to your resting potential. Now, what happens in the resting potential is now that it has repolarized enough so that it can respond to another stimulus. But unfortunately, the problem is that we have a lot of calcium in the cell, we have a lot of sodium in the cell, and we have a lot of potassium outside the cell. So during phase 4 is really when you start to have the sodium-potassium pump try to get the sodium out of the cell and the potassium back into the cell. And basically there's 3 sodium ions for every 2 potassium ions. So 3 sodium ions are pumped out. 3 sodiums are out. 2 potassiums are pumped into the cell. And this occurs during phase 4. Now there are, I don't even know how many, but there must be, I don't know, hundreds of thousands, millions of potassium pumps on a cell membrane. I don't know how many, but there has to be enough to really get all of those electrolytes back to the proper side of where they need to be, because you need to get a lot of sodium out and a lot of potassium back in. There's another pump that actually works with the calcium, but we're not going to worry about that one right now. The sodium-potassium pump is the one that we usually discuss in this case. Now, all of this occurs during phase 4, which is the resting phase, the phases between the two between all of the depolarizations. So let's go ahead and review this right quick. The first phase that we want to talk about is phase 0. Okay, this is your resting. This is your threshold potential. And of course, what happens in phase 0, you have an electrical impulse right here that depolarizes the cell to reach threshold, and then fast sodium channels open. Sodium rushes into the cell, and fast sodium channels open, and sodium rushes into the cell during this time frame, causing the cell to become depolarized, which means now the inside of the cell becomes primarily positive. Up here you have your fast sodium channels close off, and then you have a slight fast repolarization, which is the initial repolarization right here. This is phase 1, and then what happens in phase 1 is calcium channels open. So you now end up with phase 2, and calcium flows into the cell, and this will occur for a little while to allow for muscular contraction to occur. As you get to the end of phase 2 and the beginning of phase 3, calcium channels close and fast potassium channels open, which allows for potassium to rush out of the cell. As the potassium rushes out of the cell, it causes a repolarization here. This is called phase 3. Okay? And as you get down here past your threshold potential, what happens is potassium channels begin to close. And then down here in phase 4, which is your resting phase, then you have your sodium and potassium pump, which is an active pump because you need energy to push the sodium, all the sodium that's now inside the cell, inside of here in the cell. You have to push it against its concentration gradient to get it out. And the same thing with potassium. If potassium is outside the cell, you have to push the potassium against its concentration to get in. So this sodium-potassium pump here is an active pump which requires ATP. And that's a brief review of the action potential. A couple of refractory periods that we're going to talk about here. First of all, during the depolarization of a cell, when the cell is depolarizing or repolarizing, it is considered refractory. So you have you're refractory if you're not resting, and that's the easiest way to put it. If the cell is refractory, it is not resting. Because once it becomes resting, it is no longer refractory. Let me see if I can explain this a little bit. In an absolute refractoriness, what happens is whenever you have an absolute refractory period, this is the time when the cell cannot respond to another stimulus. So what happens here is the cell is already depolarized. You can't depolarize a depolarized cell. Going back to the car analogy, if you turn the key on and the engine starts and the engine's running, what happens if you turn the key again? You get that really bad grinding noise. What that means is you can't start an engine that's already started. So the absolute refractory period is a time frame whenever the cell has depolarized, and you can't depolarize it again because it's already depolarized. So it may receive an impulse, but nothing's going to happen because it's already depolarized. Now, the difference between the absolute and the relative refractoriness is the relative refractory period is when the action potential has gone on long enough that the cell can now respond to another stimulus, but it is not resting yet. So what this means is that the cell has begun to repolarize, but it hasn't quite gotten to its resting state yet. Usually this occurs, the relative refractoriness is phase 3. So this should all look familiar. We just talked about this a little while ago. So what happens is, here's your phase 4, there's 0, there's 1, there's 2, there's 3, and here's 4. So here's all your phases. Okay? So what we have here is the absolute refractory period begins right here when it actually reaches threshold and starts to depolarize. Once your cell gets up here, it can't depolarize again. Now, it's not refractory if you're resting, but as you start to repolarize, you do end up with the ability to depolarize again. Now, where in phase 3 this occurs, I don't know. I'm just going to pretend that it occurs right here. So from this point here to this point here is considered your relative refractory. Supposed to be refractory. This right here is your absolute refractory period. So here you cannot depolarize the cell again. It's already depolarized. But as you start to repolarize, what happens is there's a very short time frame here during your repolarization before you're resting that if this cell receives an impulse right here, it will depolarize again because enough of the ions have shifted enough to where you've actually repolarized enough to respond to that stimulus. Now, once you hit this point here, all the way to this point here, you are no longer refractory. You are now resting until you receive that impulse. And then once you hit this right here, this becomes absolute refractory until you get, and I'm just going to draw a line right here just for fun because I'm not sure exactly where it occurs. This is your relative refractory period. Now, this process is repeated countless of times during the whole cell-to-cell depolarization. One thing to note about this depolarization pattern, though, is that this occurs primarily in the muscle cells. A nodal cell or a pacemaker cell, like the one found in the SA node or the AV node, doesn't have the same pattern. That pattern we will actually talk about later. But if you understand this pattern right here, then you should be fine. One more note about this cellular depolarization pattern. Please remember, this is an overview of everything that occurs. There is a lot more slow channel leakage of potassiums and calciums that if you end up going through higher level biology classes, you will end up seeing more of what's going on. You will learn a lot more about it. There's a lot more information to it. This is a very brief overview. Please keep that in mind as you do go through this material. If you understand it at this level, though, it will make a huge difference when it comes to electrolyte disturbances and how a cell depolarizes. Thank you.